So yeah, we can't walk past the life cycle. It's fundamental in achieving long-term success. All of this in the end we have to package up into a strategy to achieve reliability improvement. And I'm going to talk about what improvement in reliability means. Now, what is that? What does it look like? How do you go about doing it? In the next couple of days we're going to turn those concepts here into a process, a defined, clearly documented technique to get all these great results as part of our business strategies. In production, we have defects and rework and scrap, and when you go looking at the root causes of that, underneath this iceberg are many, many root causes. Bad procedures, failing equipment, wrong specifications. There's heaps of reasons that we have problems in our production plants. On our machines, the same thing. If I have cavitation in the machine, if I have vibration, noise, temperature, I've got wear debris in my oil, by the time I see this, my machine has already failed. It's on this way to failure. Now, by the time I see these things in my P and F curve, my machine, she's way down here. My P point was back there. My F point is not far off. So by the time these appear in my machines, she's already beginning to fail. I'm on the curve, and the curve will continue downwards, or if I'm unlucky, the curve will go like that. It'll fail tomorrow as opposed to in 2 months' time. This one here, immediate breakdown. She's stopped right now, guys. Just pour the money in there, rush, get the plant back in operation again. Just do whatever you've got to do, and the dollars go up and up because that's exactly what we're going to do. We've got no other choice. So I don't want to go there. If I want to stop this scenario, if I don't want to have these problems, I've got to come back down underneath. I've got to come back down to the root cause. I've got to come down and say, well, I am getting noise and vibration because the machine is unbalanced. Its lubrication is absolutely full of water and junk particles. So if I want to stop this, I've got to make sure that these things are done right. Because if these are done right, the lubrication's clean. If the seals are secure on the shaft and there's no leakage, if I use the right tools, if my bearings are properly installed with the right clearances at operating temperatures, then I don't get these problems. So I want to not have this situation by controlling the beginnings of the problems down here. In fact, ensuring that there is no unbalance, that there is great shaft alignment, that our tolerances and instructions are spot on. And if I can control this and get it right every time down here, then these will never happen. If I get it right down here, then scraps and defects and waste and overruns don't happen either. Now, this particular philosophy it's not new. It's called Six Sigma. Been around a long time. Even before Six Sigma had a name, it was known as quality control, quality management. So we've had this around, these solutions have been there for many decades now. And lean is an example of decades. I mean, Toyota began lean back in the 1950s. And this paid off very well for them, and the world has now begun to adopt the smart solutions that lean gives us. What we do know, if we want to begin decreasing our failure rates to go from a 2 sigma world to a 4 sigma world to a 5 sigma world with less and less human errors or less and less errors, there's a way we have to follow. There's a particular sequence of activities. In a normal business that doesn't have anything more than, say, your average quality procedures with your guys, the average trained guys, average trained managers, doing the best they can, what we find, we get an outcome where we have typically between 3.5 and 2 sigma frequency of errors in that business. Now, this is trained people, trained technicians, tradesmen, artisans, MBA managers. And this is guys that have been through the ropes and learnt what they're meant to learn. And still the business delivers between 3.5 and 2 sigma. Too many errors. When we begin to stand, then the next step to reduce that is we have to systematise our processes and standardise our procedures. At this stage here, we're moving from a higher number of error rates to a lower error rate. Now, Boeing and Airbus, what do they give you? They give you a standardised procedures in a systemised way. They're one way and one way only to maintain and fly their aircraft. So they've moved from trained people with average processes into a systematised and standardised process. As a consequence, the error rate goes down. We are trying to go the next step and develop more perfect processes. Because as we standardise and have one way only, we can reduce the errors and control that process. And once we make a system of that across the whole business, once everyone does it the same way, then we are producing a situation where it is controlled. We have a controlled outcomes of known quality, and we can repeat that forevermore. So we began with trained people. We go into ISO 9001, which is now being thrust down companies' throats across the world. Better than that is total quality control. And there's one more on top of that. And the one that we promote in plant equipment wellness is an accuracy controlled enterprise. We're going to talk more about this in the coming days, but the whole point of accuracy controlled enterprise is literally that. Please, Mr. Manager, explain to me exactly what right is. What is the right outcome? And then teach me how to do that every single time. And because it is done the same way every single time, I will produce the same outcomes every single time. So this goes even further and tries to combine all the previous good practices into a new way of tackling this thing, of tackling our work, that is systematic and one way only. So if I've got 100 technicians in my maintenance crew, there's only one way to maintain this pump because it's written in the procedure. Is the procedure to maintain the bearing of a pump, to maintain the impeller, to maintain the shaft, to maintain the mechanical seal. Only one procedure, and 100 guys use this one procedure the same way every single time. So now I've moved from trained guys to business processes that control human error to business-wide processes that go across the whole life cycle of the business. And then we're going to adopt the Boeing and Airbus approach. Doesn't matter who does it, doesn't matter where they are in the world, there's only one best way. So we're going to find the best way and lock that into our company's strategies forevermore. No matter who comes through that front door, a new guy, a guy that doesn't even speak the language, he's going to be taught this one best way. Now these 100 guys, they're a resource to improve the best way. I don't want my guys to just be monkeys and follow my one procedure, because I know that one procedure, the first time I've written that, I can't be right. I can't write a perfect procedure straight off. So I'm going to challenge my guys, all 100 guys, and say, guys, find a better way. Here's our start. We're going to start with the beginnings of our improvement process that will go on forevermore. And I want you guys to take my one best way and make it your one best way, and then his one best way as the years go by. So we're not going to have one rigid only solution. We're going to do what Boeing does. When the airplane falls out of the sky, we're going to investigate what the problem is, find out where the defect was in the previous processes, go back, fix that defect, change the documentation. The documentation now goes worldwide and now across the whole world. From that one failure, the whole world is improved. So yes, I'm going to take the same thinking, but one document that 100 guys now work on to improve. And by crikeys, I bet you in 2 or 3 years' time, that thing's going to fly. You're going to have a fantastic process that everybody's bought into, everybody's helped improve, everybody knows and understands and wants to find an even smarter way again to do it. And I want that. I want to challenge my guys to come up with smart answers because everybody wins that way. They win, the company wins, the customer wins, business wins. This table is just to talk a little bit about how we grade failures, I guess. The sigma values, the ranking. That an error doesn't necessarily imply a failure. I can make a mistake and not lead to a problem. The trouble is that mistake is sitting there forevermore and I have no idea what the future is going to hold. And that mistake might one day lead to a breakdown. So yeah, the fact that we all make mistakes doesn't lead necessarily to a failure, but the defect is sitting there. And if opportunity lines up, if those Swiss cheese holes line up, and through one of my mistakes, then that day we have a problem. I mentioned before that companies actually create their own failures. That example of that guy rebuilding the bearing in that workshop, no doubt the rebuilding process, the fact that their managers and supervisors and engineers and he are causing those failures doesn't go straight past people. They don't see it. What I've done here is I've taken Edwards W. Deming's approach and begin measuring process outcomes. You look at Deming's book, Out of the Crisis, and he talks about every process leaves a footprint, leaves a message of the outcomes of that process. Now, whether you're a business process, a maintenance process, a manufacturing process, we can begin seeing if that process is a stable process in that business. What I've done here is, this is the breakdown hours of a company across 16 weeks. And I've just plotted those breakdown hours on this graph here, on this chart. And I've then gone and modelled it using the Deming approach of a 3 sigma tolerance across those results. And what Deming says, if you can model the outcomes and they are within a 3 sigma curve, then you have got a stable process. The business runs that way all the time, and it is making its own failure rates. And in this case, the worst hours are well within the 3 sigma boundary, and that tells me that this will always happen in this company forevermore, because this is the result of the way the company runs. So one of the things we want to do in plant and equipment wellness is go out and begin measuring companies' outputs, process outputs, whether it's a maintenance process, a production process, an engineering process, an operations process. If I can plot those outputs and it creates this stable range, then that is reflecting it's stable. It is something the business naturally produces. It is always there. So in this case, this company has an average of 31 hours of breakdowns each week, plus or minus 3 sigma. Some weeks have nightmares, some weeks things are pretty much okay, but every week is all over the place. And it will be that way forever unless they begin addressing the process that is causing these problems. If they want to come down to only 10 hours a week on average, then they can't do it with this process. This process they're using, the choices they've made, the people they've got, the tools they use, the decisions they make as managers and supervisors, delivers this range of outcomes. If I want to have from 31 down to 10, I can't do it this way, because this way produces that. To get down to 10, I've got to change the ways that I run the business. So the ways I now run the business in future produce 10 as an average, plus or minus 3 sigma. And so I've got to change the company, because the company is making its machines fail because it's got a stable process of defect creation, of breakdown creation. So in plant wellness, we're going to start measuring to see how stable the process is. Because if the process is stably and it's in the business and those outcomes are always coming through, it's because of the choices the business made in the past. And those choices all come together, and they're coming together in a bad way that's costing us a lot of money and a lot of downtime. With that, I can go to a manager and say, look, here's the world you now live in. This world that's costing you this much money, this much downtime, because 70 hours of production lost when it could have been uptime making product to sell. That's a lot of money you could have made had you not had that breakdown. So I can begin putting a cost to the particular way they run their plant.
Would it be correct to say that some procedures like Six Sigma and reliability-centered maintenance and perhaps others are not compatible with PEW?
Perhaps I wouldn't say not compatible, I would say not optimal. They will not produce as good a result as PEW will do. RCM, reliability-centered maintenance, many companies have applied it and have had more success. They've reduced the average breakdown rate to lower levels. So it does deliver results. But because it's not risk-based, because it doesn't actually quantify where the risks are and how the risks can arise, they never go down to the level of controlling the lower causes of what leads to those failures. What happens, they try and stop these problems here with reliability-centered maintenance, but they don't ask you to decide what requirements these must meet so that these problems do not arise. They wait for these to appear, then they go back down and solve these problems. In PW, we say, look, we want to stay down here. Get this right all the time. Have no chance of these arising in the first place. And so RCM, yes, RCM will help, but it will not go as far as PW will take a company. And PW will take a company right down to these low levels because we approach the entire life cycle and the entire company. Whereas RCM is about maintenance and what maintenance does. And that's a small part of the solution, a very small part. And we want to have a system that picks up the whole business across its entire life. And if it can control the entire business systems, then because every system's working properly, the outcome of every system's results is very much less failure. So I won't say no to RCM. If a company is keen to do that, great. It just isn't as good as it can be. Can be much better. So back to this particular diagram here with my failure tree, and if we work at this level here, for example, our photography camera, good technology, very low cost technology for condition monitoring, this is wonderful. Now this one here has done us a great service. It's picked up this hot joint here, and now we can fix it. I can fix this hot joint. The trouble is that hot joint is now going to require a shutdown. I'm going to require maintenance costs. I'm going to have to stop the plant from producing for a period of time. Why was that hot joint there in the first place is the question. If that hot joint had not been there, then there'd be no reason to do any repairs. Though we can fix it, though it's going to be solvable, the whole point is it should not have been there in the first place. Had we got our tolerances and instructions correct, had we been compliant with our fastening requirements, that hot joint would never have been there. So though we can find the problem and fix it, my issue is there should have been no problem there in the first place. I'd rather build a process where there are no problems to fix, because that gives me maximum productivity and maximum return on investment. Same with vibration analysis. Vibration analysis guy, he'll find a noisy bearing. He'll tell us, this motor's in trouble, you've got 2 months to go before it fails. That's wonderful. I've got a noisy bearing, high vibration, now I've got to maintain it, I've got to repair it, I've got to stop production, I've got to spend money. Had there been no unbalance, had there been correct alignment, had there been proper lubrication, no contamination, there would have been no hot bearing, would have been no noisy bearing in the first place. And PW is about working down here and staying down there, making sure things are right and are always right. So we don't have these troubles. Yes, we can fix them, but now this is maintenance, this is cost, this is downtime. And I don't want to go there. But if that happens to me, then I've failed. I want to be down here, lubrication right, seals right, no contamination, no unbalance, proper compliance of materials of construction, proper alignment, all the things that bring success. I want a process that brings success no matter who runs that process, and that's the idea of PW. Chop out the roots of failure by ensuring that nothing goes wrong down here in the first place. You only get this when something goes wrong there. And if we get this right and keep it right, these things never happen. And that's reliability, that's world-class performance, and that's what we want in every company. So I guess the big picture that we're trying to achieve is a world where many things happen. Sometimes they're okay, many times they're not, into a world where no matter what we do, this process produces a very tight band of the outcomes that we want. And that process will always give us proper balance, proper lubrication, proper alignment, proper bearing fits and tolerances. Automatically that process gives us those results. If I can get down to an accuracy where that is guaranteed, then suddenly I can control the time, the cost, and the quality. Because when I'm that narrow and that well controlled, these are givens. These will always happen every single time because the process is repeatable no matter who does it. And it will give me those outcomes with certainty. So, as mentioned before, the very first time I write a procedure, it won't be right. I can't be right the first time. But I'm going to start by writing what I think is best. I'm going to run that through our guys. We're going to let the guys try these things. They're going to feed back to us what they learnt in running that process. I'm going to improve it in the second draft. We do a third test and a third trial, get the feedback from the guys. And on we go and improve and create what was a wild place of unknown outcomes to a defined place of known outcomes. I'm going to take in new ideas from anywhere. I don't care whose ideas are. If they give me this outcome, I want that idea. New technology, I'm going to take that on board as well. So I'm going to be out there looking for smart answers, new solutions, because I want to grab those and turn my process even more and more fine, more and more tight. Because I know the more precise I am, the more reliability I get, more profit I make. And then these things are no longer out of control. I know what they will produce every single time. So we're going to standardise, we're going to systematise, we're going to challenge people to improve that continuously forevermore and drive this band of success tighter and tighter and tighter, repeatable, with more certainty, because we will then get these every single time without question. Same story. So in the end, reliability is about a quality control issue. What quality must I achieve that when I achieve it produces this reliability? Because the standards that you set and the standards that you meet is the reliability that you create. So reliability is totally manageable. You can get whatever reliability you want because it depends upon how fine you want to work to. And the finer you work to it, the more control you apply, the more certainty of the known outcome you're going to get. So this idea of the accuracy controlled enterprise, that's accuracy controlled enterprise. So what is the accuracy I require to produce the uptime and reliability that gives us maximum profit? Then how do I achieve that accuracy and control every single time? And this is where the 3 T's come into play. The 3 T's, target, tolerance, test. I need a target to shoot for. Now, what is the perfect result? I'd love to have a perfect result every single time, but the world is variable. There will always be variation. There will always be a distribution curve. So I've got to limit a distribution. So I have a tolerance within which I will work, and outside of that, which I will stop and actually address the problem. And we know now our carpenter's creed, that test, that second test, is vital because that's the one that brings reliability. So the 3 T's, literally a target for precision, a tolerance to give us quality, and a test to give us reliability. And if I can do that in our documentation, then I've built a process that can be followed by anybody that takes that document, and I will then be able to produce the same results every single time. This particular slide's about standards, and it's about the standards of lubrication management. This item here is a part of a spool piece on a steam turbine in Australia. You'll notice just in here that there's a ragged section where the spool that ran inside there, the spool jammed. That lubricant used to control the hydraulics that drove the spool up and down inside the cylinder was as clean as an 1816-13 ISO count. Now, if this means nothing to you, that's part of the problem. Because that ISO count number is vital to understand if that lubricant is in a condition that is safe to use. Let me explain. 18, 16, 13, it's ISO 4406. In that standard is a table that tells us what these numbers represent in terms of actual particle count. This one here is all particles greater than 4 micrometre in size on the longest length. This one here, greater than 6 micrometres on the longest length. This one here, greater than 14 micrometres. So we now have a way to take a sample of oil and count the particles by size and the distribution of those various sizes in the lubricant. This company, when this problem happened, was an 1816 particle count. And that count was the OEM's requirements. The manufacturer of the equipment said you must have nothing more than that, and that's what it was. And that count caused that. So this lubricant is too dirty to get high reliability out of this machine, even though the OEM said it's okay. And what we'll find is the OEM's requirements are not good enough for reliability. The OEM's requirements are acceptable, tolerable, sufficient, but not good enough. They aren't in that boundary of precision that provides high reliability. So we have now a way to count our particle count. And literally, they take a sample of oil, they put it through a machine, the machine shines light up there and it counts the black dots. And the black dots eventually come out to an ISO count of that order there. What's important here to know is the number. And the question I'm going to ask is, what standard do we have to achieve here? What's the count we need to achieve to ensure that this problem never happens again? Because at 18, 16, 13, what the OEM recommends, it will happen again and again and again across the whole world. Because that's the nature. Now, once I select that, I will have wear particles in there. And every now and again, those wear particles will jam up somewhere in the spool and another machine goes down. And that's a process choice. Someone chose to have 18, 16, 13. What we're beginning to find now, there is a magic number. This 18, the worst it should be is a 14 value. At 14, 13 and 11, same size lubricant batch, no wear particles in this sample. Now, there will be wear particles in the whole circuit, but very, very low numbers, right down to the hundreds per millimetre. Here we're in the tens of thousands per millimetre. So between 40,000 and 80,000 particles in a millilitre of oil. Millilitre is about 20 drops. So 80,000 particles of this nature in 20 drops of oil. Here in 20 drops of oil we're down to only 160 particles. So this here is, each of these black dots is an opportunity for a failure. So high opportunity of failure here, high risk here at this level. Here, low risk, because there's not much opportunity for failure. Not one, not zero, they're still in there. But because they're so dispersed now across a large amount of oil, the chance that that will jam up in here in enough numbers to actually cause this to seize, very unlikely. Whereas here, there's enough numbers to cause it to seize. And eventually, every now and again, the dice roll and come up the wrong number and the machine goes down. So, we've taken that information. I just need to bring this a little bit up in size. This is actually a laboratory result of a company in Australia, and the lab result comes back with a 23, 22, 19 count, which is interesting. It's a number. That's what it is. Now, this particular machine, this oil sample was taken from a hydraulic circuit in which that pump is the driving force for the hydraulic liquid to move around that process. So I go back to the OEM's requirements, and the OEM's manual says your oil must be no more contaminated than 18, 16, 13. But hang on, it says 18, 16, 13 is the worst it's allowed to be, and I've got 23, 22, 19. Does that bother you? Yeah.
Yes.
It bothers me now because I was told the worst it's allowed to be was this 18, 16, 13. Once I know the standard required, even though this standard here is the OEM's requirements, once I've got this figure here, I can begin to compare everything else against that figure. And when it's above that figure, then I know that's beyond what it's meant to be. So once, if I have no standards, if I have no engineering values to measure, no values to compare against what result I get, then this number means nothing. This machine is a 40-year-old machine. It is the most breakdown-prone machine in that company. This machine is always down. Hugely expensive machine. Has been for 40 years. Why has it broken down so many times in 40 years? It's been dirty oil from day one. For 40 years, they have not realised what's making that machine fail. They're better now. I mean, this is why they had me in there to learn what the trouble is, and now they understand that this is disgustingly dirty oil. Pitch black. I get a sample of oil in a little container, and it's pitch black oil, full of muck and rubbish. But for 40 years, nobody questioned that. And the answer was always there. It was always there in the manual. So I've got to have a standard. I've got to have a measure against which I can grade what it is right now. And that standard has to be a measurable engineering figure that is indisputable, undisputable, once that result comes in. Knowing now that's very dirty oil and it's actually causing the machine to break, I can now ask some smart questions. I can begin looking at some solutions that will actually solve our problems. And this is what this chart on the side here is all about. Back in the 1990s, in Britain, a survey was done across about 120 manufacturing businesses that have hydraulics equipment in their plant. They took samples of oils from these 120 companies and measured the contamination in the oil and began to grade the life of that machine against the oil contamination. And what they said is, we'll just take 18, typically the recommended OEM's value, and call that one life. So an 18 count value, and 18 is the first number, because this first number is every particle of that size and above. So it picks up every single particle. That's typically of a big enough size to be a problem. So an 18 at the very beginning gives us one life. 23 at the very beginning is a quarter of the life. If I come down to 14 at the beginning, 3.5 times the life. And what that's saying is the cleaner you have your hydraulic fluid, the longer you will have between failures, because the wear particles that cause the failures are not there to cause the breakdowns. And if I get down to 12, I will get 6 times the life. Get down to 10, 19 times the life. And nothing's changed, the same machine, but now very, very clean oil. So lubrication management to me is a no-brainer. If you've got mechanical equipment with hydraulics or lubricating oil, then the answer is very, very clear. I've got to drive that contamination down, 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 down. And I will get back much more service life. 4 times less breakdowns, 6 times less breakdowns, 19 times less breakdowns from hydraulic oil failure or from contamination failure. And all that comes from understanding what this standard is. 18 is a number. Is it good enough? No, it's not good enough. It's the bare bones requirement the OEM recommends. Not good enough for reliability. Just reliability is down here, 14 and below. I get 3, 4, 5, 10 times the life. So I want to build a business process that drives me down this scale, because the further I go down, the more and more life I'm going to get, and very cheap, very cheaply. It's not going to cost much money to get that sort of life. So standards become vital, because without them, I'm blind. Without them, I have no idea what's going on. Once I've got a standard, if I'm worse than that, then I know something is wrong. I've got to find that cause. And if that solution is not good enough, I can get better and better solutions, because the more precise they are, the cleaner my oil is, the more accurate my tolerances are, the longer my machine parts will last. And that means reliability. Another case study of what it means to have a standard is our head pulley on a conveyor. This particular company, inside here, every couple of weeks to 3 weeks, they'd be out in there again, pulling that bearing out and putting a new bearing in there. The bearings in here never went more than about a month. And they should go many, many years trouble-free. So something that's being replaced every month, something is seriously wrong, in a big way, in a real big way. Now, this particular bearing was on a tapered sleeve, and it was a spherical roller bearing, quite a large one, 6 inch. This shaft's actually a 6 inch shaft, 150mm shaft. This company eventually called in the bearing manufacturer and said, look, this is costing us an absolute fortune. We don't know what's going on. Can you please investigate? The first thing the bearing manufacturer said, micrometer the shaft. Go out there, next time it fails, take measurements of the shaft, where the bearing sits, not the whole shaft, just where the bearing sits, and here's what they asked them to do. So in 3 planes where the bearing itself would sit, take those measurements at 0, 45, 90, and 135, and this is the requirements they must meet. This shaft is 150mm, 6 inch, so between 120mm and 180. It must be a H9 tolerance, and it must have an IT5 form. Both the tolerance and the form were given in the catalogue of the bearing manufacturer. This shaft must meet those requirements to get full service life out of our bearings. If it doesn't meet those requirements, you're going to have degraded service life. So now they've given some standards. The standard here must be H9 and better than 18 microns form. So I'm just going to go into the workbook again and take this example a little bit further. There's my case study. Yeah, there we go. All right, so we've got that same drawing up here, the same image. So we're here on that particular row there, and the requirements are a H9 and an IT5 form. Let me explain what H9 is. Now, if you're a mechanical fitter, if you're a mechanical engineer, if you're an engineer of any sort, and this doesn't mean anything to you, then that's part of the problem. Because this is the language of reliability, this is the language of machine design and manufacture, and if those numbers mean nothing to you, then you've got an education process to develop yet, because that's vital language, vital knowledge that is part of the solution to stopping these problems. H9 says must be between 150 millimetres exactly and as small as 199/900. And an IT5, International Tolerance Grade form number 5, that's how they actually set the tolerances on shafts and on housings. The International Tolerance Grade numbering system is how they specify how finely to make the various parts. And it must be an IT5. So no more than 18 microns error beyond the exact value is what that says. I'll show you in a second what that means. So let's go down the page. So we've taken measurements now and our various planes at the various angles. And these are the actual results with the micrometer. And this is what the guys measured at the time. And we can just check, is the tolerance acceptable? Is everything within 150 and 149.9? And there's nothing there. 149.98 is the biggest, or 0.99 is the biggest, and the smallest I think is 0.94. So it is in tolerance. That shaft satisfies the first criteria asked of that shaft to meet. Got one more thing to check. It says to check the cylindricity. Now cylindricity, if I sketch that thing out roughly, what it's saying is that cylindrical enough to be acceptable? And we have an 18 micron tolerance. 0.018 millimetres. That cylinder, or that shaft section where the bearing sits, must be cylindrical enough to be within those boundaries. Outside of those boundaries, it isn't cylindrical enough to take the bearing and sit it properly. So again, the same measurements. In this case, we had plane A. It was plane A, B, C. And what it's saying here is at plane A, B, C, at the 0 location, here was our 0, 45, 90, 135. So along that line there, the measurements along that line there. And at the 45, the measurements along that line across the back, and the same across the 90 degree there. So is it a cylinder? We're measuring along the cylinder in that case. It must be less than 18 microns. In this case, along the 0 line across the top, yes, 10 microns meets requirements. At the 45, 50 microns, 90, 30 microns, 135, 40 microns. This shaft isn't a cylinder. It's not cylindrical enough to give full service life of that bearing. We can check one more thing. Is the roundness. In other words, is that section here actually round? Same story. I have 18 microns to work with. There's an annulus here, imaginary annulus of 18 micrometre. As long as I'm within that annulus, it is cylindrical enough, it is round enough to be used. In this case, plane A is round enough, 10 microns, but plane B and plane C are 40 microns. Twice as bad as it's allowed to be. Fundamentally, this shaft looked like that. So when the bearing sleeve went on, the sleeve went on like that. On the top here was our outer raceway that sat on the sleeve, and of course we had our rolling element in here. So every time the rolling element goes over this gap here, this sleeve flexes down, flexes back. 3,000 times a minute if it's a two-pole motor, depending upon how many elements there are in there as well. So that's why the bearing was failing within a couple of weeks. This gap, because the shaft is unsuitable for the job, was allowing the whole bearing to flex. Eventually that would fatigue very, very fast, and of course it breaks. Now that was repaired and repaired and repaired. Pull the bearing off, put the bearing on. Pull the bearing off, put the bearing on. Every 2 weeks to a month. Pull the bearing off, put the bearing on. For years. What's the guy thinking? How can you keep doing that year after year after year? Obviously the guys maintaining that didn't understand. Didn't understand what it was saying, because nobody measured this. Nobody ever measured this until the guy came in from the bearing manufacturer and said, please tell me how round, how cylindrical that shaft is. Should have been the very first thing that was done. After the very first failure, somebody should have measured the shaft to make sure the shaft was round enough to take the bearing. Had they known, hey, got to meet IT5 and got to have H9 tolerance, if that had been in their documentation, it had been a procedure that says measure the shaft and record the values in this table and compare it against the known acceptable values, we'd have seen it right away, straight away. So I need standards. I need an engineering value that I can measure against which I can compare the current state against the ideal state. And if the current state is away from the ideal state, it will cause failure. And without that number, I put the bearing on, I pull the bearing off. I put the bearing on, I pull the bearing off. And I will do that forevermore, because nobody's asked me to measure. Nobody's asked me to compare the current state against the ideal. And of course, over time, things fail and continue to fail. And one wonders why. Why is this thing failing, costing so much money? My guys that are out there maintaining it, they must know what they're doing. Well, they were taught the wrong way 20 years ago. And have been doing it the wrong way for 20 years. And this is the bit that confronts us in companies. The answers have been there a long time. Why aren't the answers in use today? This solution's been there 100 years. That problem's a 100-year-old problem being fixed 100 years ago. And yet, companies still don't do the right thing. So, Planet Equipment Wellness is to go out and find the right thing to do and bring it in. Don't wait 20 more years. We haven't got 20 years to wait. Haven't got 2 years to wait. Get the answer, bring it in. If I've got to argue with the manager, I'm going to argue with the manager. Here's the cost against the risk matrix. Here's your current risk now. Let's bring in the right practice, bring in best practice. Going to drive your risk down to here. You're going to make a lot of money. Here's how you're going to make that much money in the triangle. So yeah, business case based upon engineering understanding. And obviously my guys need to be trained up. They're good people. They're doing their best. You know, these guys, they want to have a good, happy life, happy job. But they've missed something. I can't blame the guy. The guy's doing what he was taught. The fact that he was taught wrong, and his supervisor doesn't know any better, and his manager doesn't know any better, and the engineer in charge doesn't know any better, that's not the guy's fault. It is a business system failure, and I blame the business. I don't blame the guys, I blame the business. And we want to solve those problems. Now, the 3 T's is this accuracy controlled enterprise concept, the ACE 3 T's. We play games. Whenever we play a game, the first thing that's always in the game is a target. Now, where is the full marks? Here in Aussie rules, Australian rules football, the full marks are between those tall posts. In American football, the full marks are between the posts. I play basketball, the full marks, we know where the full marks are. I play archery, the full marks are very, very clear. This one here is an interesting one. This is in Amsterdam. It's a public urinal in Amsterdam. And what it was the floor was always wet from people using the urinal. It was dangerous because it was slippery. So they actually etched a fly. That's actually a fly. They actually got there and etched the fly in. 80% improvement in less water. You put a target up and we're going to shoot for a target. So I want to have a target wherever I want to start controlling things. The first thing I've got to put in terms of control is a target. Where are the full marks? Now in engineering, we know that tolerance is part of the world. There will always be a degree of variation. In engineering, we specify our drawings to be within a tolerance of size that is sufficiently accurate to do the job that part's meant to do. So again, tolerancing is something that is expected in engineering. It's normal language. Even in archery, this bullseye is actually a fairly big dot. It's a big size thing. So we're going to have a range of points that still give us full marks. So we get a fairly good tolerance for a decent sized bullseye. So I need to have a target to be clear of where the ideal result is, but I've got to respect the fact that the world is imperfect and there's going to be a degree of variation. It's how much variation I want to control, not the fact that there won't be any variation. When it comes to measurement and testing, we do this all the time. We can measure our eyes and test our eyes, and we can measure company performance. Here in our production processes, we use control charts to confirm how the process is behaving. In engineering, we use measuring devices all the time. Even in our foods, we can grade our foods and pass the beer for consumption, because if the beer is not contaminated, then because there's no contamination, it means it must be okay to go out and sell that beer because it's in a condition to be saleable. So target tolerance test is stuff that we've been doing all the time. What I'd like to do is take that concept of target tolerance test into my procedures. When it comes to accuracy control, I'm going to have to define the specifications that give me the accuracy I want. Because in the end, I'm trying to build a process that was like this, with many possible outcomes, into a process that is very, very tight and narrow. And that will eventually come down to the one best way. What is the one best way that gives me this control, that removes all these possible outcomes, and now I only get what I want? So I'm going to come down eventually to a documented process that has standards of quality, that if I achieve those standards, produces that result every single time, no matter who runs that process. So in my documentation, in my procedures, I want to have a target. What is the best result I can ever hope for? Because if I can deliver that target every single time, if I can deliver a bullseye every single time, give me a bullseye, because that's the best result we can hope to achieve. But the world is imperfect, so I want to have a range of what's acceptable enough. So I'm going to have a tolerance, which I call good, and the target I call the best, and in between is the better. So I go from good to better to best, and typically better is a stretch target. It isn't as good as the best, it's in between. Typically halfway would be a place to start, but it wouldn't have to be halfway. And of course the test, I must have a proof test. The proof test is vital to bring reliability. So in my documentation, I'm going to give the guys all that they need to know to get it right, to make a repeatable process. Then I'm going to do one more thing for them. I'm going to say, if your result is outside the range of tolerance, do this. So I'm going to tell them here, if your result is out of that tolerance, do it this way. So back up here, when we had our shaft and the tolerance was unacceptable, in my procedure it would say, okay, if the shaft is not H9 or not IT5, replace it. Or take the shaft out, go back to the workshop, machine a sleeve up and re-sleeve. And then we'll buy a new shaft for you next time we have a shutdown. So I want to tell the guys what to do if it's out of tolerance. If it's in tolerance, we're going to use it. Out of tolerance, I advise them what to do, because if I don't tell them what to do in the documentation and they're out there on that plant and they're maintaining that machine and they start pulling the bearing off and measuring up and saying, gee, this shaft is no good, now what do? I'm under stress. As soon as he finds a mistake, an error with that shaft, he looks at his clock and says, gee, to fix this is going to cost me half a day, going to cost more money, going to cost more production time. Then the stress builds up in the guy. And he might say, you know what, it's close enough. It's close enough, we'll put it back in service again. And that's a mistake that that the company's allowed him to make, because we haven't advised to him what he should do if it's wrong. So I'd rather tell them here in the documentation, if this shaft is not round enough, here's the two choices. Do one of these. And if it's still no good, call me. Call me out of my office, I'll come down and we'll have a look at it together and work out what we're going to do. So I want to take the stress away from my guys. I don't want to put my guys in emergency situations. If there's an emergency situation or a high stress situation, they will make the wrong choices. We saw it from the human error rate table. So as a business manager, as a maintenance manager, I want to keep my guy's life real simple, real clear, real easy, real straightforward. Just follow the rules, guys. Here's the rules. 1, 2, 3, 4, 5, 6. Here's the rules. Just follow the rules. Keep it simple to yourselves. So I want to think about this in the clear light of day without the stress of being in this situation. But when the situation arises, here's the answer. And the guy just follows the answer because that's what I want him to do. And he knows is what I want him to do because this process was actually built properly with the intention to create this outcome in this use. Now the 3 T's conceptually, they produce a target. I've tried to give you an image of what's actually happening here. So here's our target in archery. We've got the different colours. So bullseye is yellow. The best outcome is yellow. The next outcome around it is the better outcome, and then the good enough is the blue. So just in terms of when we have a good, better, best, and that could be gold, silver, bronze. I don't mind how you call those or any other words. The whole point here is what is the target? What is the quality that gives me world-class performance? Please tell me that. Because I'd like to achieve that every single time. But I will accept something that is passable. So anything on this side is a pass. Anything on that side is a failure. So with the 3 T's, we have a very clear definition of what's pass and fail. I'd like to get world class every single time. So I'm going to tell you what world class is because that's what I really want you to do. I want you to hit a bullseye every single time. But I will accept good enough. Good enough isn't, we know that, it isn't good enough, but it's what we are today. And typically what I say to companies, set this value here as what the OEM sets. Whatever the OEM says is acceptable, do it. So if the OEM says that, 18, 16, 13 ISO count is acceptable, do that. So this figure here is 18, 16, 13. We know it's not good enough. We want to be here, 14, 12, 10, whatever the case is. So I'm going to have 14, 12, 10, maybe even 12, 12, 10, 9, depending what I want to do in terms of pushing the limits. But what the 3T does is create this mental target for us to shoot. Creates a challenge for our technicians. I'd love our guys to know where the bullseye is and to hit a bullseye every single time. Because if the guys hit a bullseye every single time, then immediately they get feedback. Our brains release serotonin. The guys are happy to hit bullseyes because they know right away that I'm up there with the world's best. And up in our brain, the chemicals change. Serotonin's released and we get this great, satisfying, happy feeling through our whole body. Great place to be. Great place to be for everybody. So I'm just trying to work with people, trying to give them the right answers. What gives us this outcome of clear results, high quality performance every single time. If you can do that, do it because it's a great place to be. At the very worst, no worse than what the OEM requires. And then if that's what we try and start with today, the day will come when that won't be good enough. And we'll move the best down the better becomes the new good, and put a new best in front here and keep driving improvement into the future. So accuracy control, there's the accuracy. We want to be there at the best. If I hit that figure every single time, I'm going to create this result, these performances, which will be high reliability in a guaranteed way, repeatable across the whole world.
Is it reasonable to think that the OEM, unless he is prodded with a customer, will never change from what he has? He has no incentive.
The incentive is reliability outcomes is high profit for a company. If we can get high reliability, we're going to be a more profitable business, lower cost, more throughput. Now, companies want that. If that is being stopped by the OEM's poor quality engineering, poor quality standards, then I'm sure you're going to tell him and say, look, I'm not going to buy any more machines from you. This guy in Japan makes it better. He costs a bit more, but he makes a better machine. I'm going to go to him next time. So I'm going to give you one more chance. So that's what will happen.
But you have to do that. If you never do that to the OEM, then he does.
Look, what it's saying, the OEM's engineers are no better than anybody else's engineers. Because if their engineers understood this, they'd be out there making good quality machines to sell to you at a good price. Because that'll keep the business and make them a lot of money. But their engineers don't understand this either, because they're setting standards that cause failure. Now, the OEM's creating a failure by setting that standard. Now, I'm sure he's not doing that on purpose to get repeat business, to buy the spare parts off him. I'm sure he's not doing that intentionally, but that's the result that your company suffers. Their lousy standards you accept as being acceptable, and it's not, but you believe it is. As a consequence, you get the breakdowns forevermore in the future. And how do you solve that? Well, you've got to have quality control. So what standards must I have? Gee whiz, give me 12. Give me 12. That will create reliability. So Mr. Manufacturer, install on your hydraulic systems kidney filtration as part of your supply to me. If you don't install it, I'm going to install it myself. I'm going to spend the money to put kidney filtration on that unit on purpose. Because that 12 from 18 is 5 less breakdowns. That breakdown of that turbine was 2 months downtime, $25 million. That company at 18 cost, the OEM's requirement at 18 cost the company $25 million and 2 months downtime in a power industry. They could have sold so much power in 2 months. They couldn't sell because the machine was broken, because the OEM's requirements are nowhere near good enough. And that's what you'll find. The OEMs think wrong. They think this is low-cost machines, I'll be able to sell that, easy to make. They miss out the fact that, hey, your customer is losing a fortune because of your poor engineering standards. So I've got to have the customer understand what questions to ask. Your specifications, what is your IT grade on your components? How do you control the manufacturer of your shafts? How do you get roundness of your housings? How do I know that your bearing in that machine isn't pinched? If I pinch that bearing with an out of round housing, I'm going to have high stress in that bearing from day one. So yeah, once we know what the right questions are to ask, you will ask the right questions. And if the answer is the wrong answer, thank you very much, I'll go to somebody else next time. And you will, because there's so much money sitting on the table that is so easy to pick up. So, in terms of managing my process and setting out and developing a process, I want to have a target for precision. I've got to have a tolerance for quality, and of course I've got to have a proof test to prove I am within the tolerance. So that's where the 3 T's come from. And I believe if we can include the 3 T's into all our tasks, into all our deliberations of what questions to ask, we're going to start hitting a lot more bullseyes, getting great results, producing processes where the outcomes are guaranteeable and repeatable no matter who does it.
You ever run into a situation where somebody says, well, you know, we can set a target and have a tolerance, but there's really not a good test. Or the test requires me to take the equipment apart. I can't run the test.
Look, yeah, that's certainly possible. What we try and do is as the guys went through the procedure, we actually put in the tests as part of the rebuild. Because if I build a machine with 100 parts, with 200 parts, and the only test I do is at the end of the rebuild, I start the machine up and do a vibration check on the noise of the bearings. And if the test shows a high vibration within the first hour of operation, am I going to pull that machine down again and find that high vibration cause? No. I'm just going to say, oh, guess what? We've rebuilt this incorrectly, but run it anyway. I haven't got time to rebuild it. So these tests have to be done during the actual process of rebuild. We're going to have hold points to do inspections and measurements against a particular standard that we have chosen. So we're going to have a test throughout that whole rebuild process. Operations throughout the operating process, we should have test points. What are the pressures? What are the flows? What are the currents being drawn by the motors? Are they within the boundary that gives us high reliability? So the 3 T's is a principle. It's a universal principle because it's going to create a process of very tight outcomes. And it's the accuracy, the quality control that drives reliability, that produces the outputs that deliver the high performance and high profitability that we're looking for. It's a different way to think. You know, it's demanding. It's more demanding, no doubt about it. You know? Guys have to be guys that can deliver this level of quality. It might require some upskilling or some reskilling. You have to buy some smart technology. You have to buy some stuff that lets us test things easier and simpler and faster, intentionally, so we can be sure that we create the results that we want. So yeah, there'll be times when it will not be easy to do, and we're going to have to find a way to solve it, or at least be comfortable that what's been done is acceptable. but it won't be necessarily easy to do every single time. But the way to think is the right way to think. Yeah, so we're going to have good is the OEM's requirements, world class should be our best, and that world class is out there. We saw it before on that hydraulic chart. The world class 14 and 12 ISO count, that's out there. The IT5 value came off the OEM's requirements. That was in the catalogue for the bearing manufacturer. I don't have to invent these. These have all been out there, in many cases, for 100 years plus. And of course, in between, I have a stretch target. The whole point being is I want to have standards that produce the quality and delivers the reliability that we want. And I want to build a company process that does that every single time. Okay, I mentioned this before. Pass, fail on the OEM's requirements. World class is what the very best are achieving. Maybe the stretch targets are halfway too. And of course, if it's out of tolerance, what do we want the people to do so we take the stress and the strain and the pressure off our guys? I guess one thing that once I call something good, at least we know what good enough is now. Once we say, oh, that's good enough, well, we've got a number that tells us if it's good enough. I mentioned before that in time, the guys will get better and better and better, and good won't be good enough anymore. So we throw good away, better becomes good, best becomes better, put a new best. Because if I can achieve this, if I can achieve that, even better again. Even more control, even more certainty, even lower costs. This particular document is actually from a work order in the same company that had the problems with our hydraulic system that we saw before. This work order is a visual inspection of their pumps in their process plant. They have a couple of hundred pumps doing different duties, but this is a common inspection they use across those pumps. Centrifugal pump, and of course the work order pops out, and this is a backing sheet on the work order, and it says to go and do this. Go out and inspect this particular pump. First check is to check pump base / corrosion / security. That's his job, to check corrosion and security. I'm not sure what that means. This to me, corrosion, is it concrete corrosion? Is it metal corrosion? Is it hold-down bolt corrosion? No, I've got no idea what he wants me to do. Next question, check pump guards, / cracked, security, adequate. What is a secure pump guard? Now, what does he mean by that? Does that mean there's no cracks at all? There's a crack no bigger than eighth of an inch? I have no idea of what quality is acceptable to give a tick to this. And down here at 6 and 7, check condition of motor and associated cables. Well, these top 5 are a mechanical fitter. A mechanical person goes out there, and now he's asked to check condition of pump, motor and cable. So the mechanical guy says, well, there's a motor, and the cable goes in, tick. Next step, check condition of stop-start station. It's there, it hasn't rusted off, the cable goes in, cable goes, tick. So this is a tick and flick exercise. Now this company will have had this work order in service for 40 years, and for 40 years their pumps are still failing. It's because what exactly is acceptable? If I pop this up into our workbook, and what this is a roving inspection. It's saying to the guy, go out and wander around the plant with this fake checklist and look for problems. Look for corrosion, look for security problems. It doesn't say exactly what corrosion means and what security means. It just sets a roving inspection with an error rate of 1 in 10. We're going to miss 1 in 10 opportunities of coming failures. There's another one here. It says this particular, as an engineer, mechanical engineer, I know what he's trying to tell me. When it comes to corrosion, he's talking about the pump base corrosion. Is the pump base still rigid enough to keep this thing operational? Concrete pedestal, is that corroded away? It's a chemical plant. Yes, the concrete can corrode. So an engineer doing this that professionally understands mechanical machinery and pumps and understands the process risks probably wouldn't do too bad. But this is a technician. This is just somebody that has just sort of learnt things along the way, has no idea of the science of a problem and the science of his processes. Now, I'm sure security means, is the pump base actually solid? Is the thing actually solid? But it's visual inspection. So it says to check visually pump security. If that's my hold down bolt, and I've got a hold down bolt there, I'm looking at the hold down bolt. Can I visually check a hold down bolt is secure? I can't. I've got to put a ring spanner on or a socket and check it physically. There's no other way to look at a hold down. I can't. So it's a dumb question to ask. Security of hold down bolts and security of base plates, no definition. This technician, if he's brand new in your company, he wouldn't even know what these words mean. An old guy, 20-year-old guy that's gone around looking and doing this check 100 times in his career, it's a tick and flick. If he's had a pump more than 5 minutes, I'll be surprised. He'll come back to you, every single thing's ticked off, and every single work order for the last 20 years will have ticks against all those, and the pump still fails. This particular business process results in no value. Unless you know what these words mean, you cannot compare acceptable standards against, well, there is no standard. I have no way of having a pass-fail criteria beyond what I remember is acceptable from somewhere else in the past. Now, that's not good enough, because that's got us to where we are today. This company's procedures have got them the breakdowns they're currently suffering. That's the process outcome of making that choice. We've got to change our processes to ones that have defined criteria. So I want to now introduce, what exactly do you mean by the word corrosion? I'm going to have a table like this, and in here I'm going to define concrete corrosion, steel corrosion, base plate corrosion, pipe corrosion, and tell them exactly what's pass and what's fail. Now I'm going to turn it into a defined criteria. And when I have a checklist with defined criteria, I have developed a process of an error rate of 1 in 3,000. So I can certainly go from 1 in 10 to 1 in 3,000 by having defined criteria. Now, that job on this pump now becomes a half-hour job. From 5 minutes, it becomes a half-hour job, because I'm going to ask the guys to do these inspections. Here are the same words, and I'm going to define what a crack means. I may even put a picture in here of what's acceptable crack and what is not acceptable crack. I'm going to make it very clear and easy to read and visually satisfying for the brain to pick up the image and the message very, very fast. This is now a half-hour job per pump. But if the defined criteria all pass and everything's in good condition, I have absolute proof this pump is actually a very good pump. I should have no troubles with this pump, because here it is. All the things I've asked him to check, they have been checked correctly. They've got the tick. He's actually gone to the right place to inspect, and his record of the evidence is very, very clear. So yes, my process has now changed into one that has far fewer problems, that has more belief in the results, but it's gone from a 5-minute job to a half-hour job. Is that worth it? In my company, I would say, why aren't you doing it already? In other companies, they might say, no, 25 minutes isn't worth it, because it'll take an engineer 2 days to write this up. 2 days of an engineer's time to get this document that is applied across 200 pumps and will be for the next 40 years. Isn't it worth it? It doesn't make any sense to me. As an engineer, manager now, that sort of logic is crazy logic. The whole point being is I can build a process, document-based process that is repeatable, that is very clear, that has the complete parameters of pass-fail criteria into my 3 T's, and I have got this error rate. I have made the world a much better place for the technicians, my operations guys, and me too. One of the things that we want to introduce for high reliability is precision maintenance. And it's good to know what precision maintenance actually is, because when it comes to mechanical equipment, it comes down to only a few things. There's typically 14 points that we tend to work around. Fits and tolerances are critical. Lubrication is critical. Distortion-free machinery is vital. Parts running true. directly in line, everything runs directly in line, so things are not out of balance. We have low vibration, we have good alignment, everything is set up properly, in line, straight. The whole point is to reduce the stress. I want a technique where the stress in my components come right down to the barest amount that is required. Because if I cut the stress down, reliability and service life goes up. So I want to have a clear concepts to adopt. So these 14 points are what we try and work on because they will produce high reliability, low stress, and as a consequence, high uptime and high throughput. Correct fastening, correct tools for the job, correct parts for the application. We want our technicians to be problem solvers. I want my guys, when they rebuild a machine, to build a better machine. You know, find the problems, repair the cause, build a better machine, and be happy with the work you're doing. Proof test to confirm all this is actually achieved. And of course, you want a system to make it automatic, systematic, standardised. And that system, of course, will be the 3 Ts and the accuracy controlled enterprise. So I want to have a good, clear indication of what I'm trying to achieve in the processes I build to maintain machinery. Now these numbers, I know that I'm going to need some values to measure against. I've got to have standards. So speaking of the table here, I set some targets. Now these targets depend upon the machine. Here I've given you a sort of a general indicator of what these targets would be. You know, running true to centre and IT5 accuracy within 18 microns across the machine length. Distortion-free machinery, again IT5. So no parts are a banana shaped more than 18 microns. Now each machine, each manufacturer, they might change. So this is representative of what we're trying to achieve. Those actual numbers depends upon the particular design of the equipment. So these aren't universal, they're indicative of what we're trying to drive towards. Tension accuracy in our fasteners of plus minus 5% would be fantastic. But I will accept up to plus minus 10% before I begin getting worried about our practices. So this particular table is giving us some parameters to work to these 14 aims. This ties back in. What are the numbers that give us this zone? Now, what is the engineering values I must achieve that when I achieve those, I'm at high reliability? That's the whole point of this. For this machine, this asset in this company, and the one over here, what are the magic numbers that create this zone? And guys, we've got to be in this zone all the time. I'm going to build a process to be in this zone because in that zone, I guarantee high reliability. Out of that zone, I guarantee lots of failures will definitely happen. So that's the name of the game. Be in here for the whole life of the machine. As a consequence, we'll have far fewer problems, far more uptime, far more throughput, far better quality, all the things that we want. But I've got to have the right numbers and make sure that these numbers are being delivered to the machines. When they are achieved, there's no misalignment, no out of balance, vibrations very negligible, design loads are where they should be and as they should be, lubrication is in top quality and tolerances and fits and temperatures are controlled. It will happen. It automatically falls out of that process. I build a process that creates that outcome and make that process live and be improved in the business. So heading towards the end of this sort of coverage of the concepts in plant and equipment wellness, it's an asset management philosophy. It's about ensuring that we get high reliability from the design point onwards. I want to get it right here because if I get it wrong there, nothing else matters. I can improve it a bit, but it's marginal. Then I've got to operate and maintain correctly for the entire life of that plant. So asset management is going to be about creating systems that deliver those outcomes reliably and repeatably. We know maintenance is part of the solution. It's not the complete solution. The complete solution is going to involve operations, engineering, finance and maintenance. There's going to be a partnership here to get high reliability. But maintenance contributes success in a couple of ways. One is reliability. We want to actually not maintain. Maintenance is expensive. Maintenance means that the machine is unreliable. So I want to eliminate maintenance. In the end, I want to minimise that to the barest requirements. And we want to do this by reducing the chance of failure, minimising the risk to the equipment so that the risk isn't there to cause the breakdowns that become the maintenance that we then have to fix. In a simple plot, compared to other strategies available, plant and equipment wellness is a business-wide focus. It's a life cycle focus. Things like RCM, it's typically focused on an asset as a physical thing. But that isn't the ultimate solution. The ultimate solution is across the whole life cycle, do the right things that deliver the right outcomes forevermore. Got to know what they are, got to find them, got to lock them into place as how we do our business in this company.
Why does the curve do this from that?
Okay. When we bring in any change, we're going to have to change the company's current practices. I'm going to have to spend some money, I'm going to have to spend time and resources to develop the procedures, to buy in the tools, to do the measurement, to do the training of the guys, to be able to do the procedures properly.
The investment first.
Yeah. So the cost goes up first, and it will do for possibly a couple of years. But the payoff, it's an investment. Great, the word is correct. It's an investment on your future, in your future. So I'm going to pay some money to do the right things, to bring in the right processes. By doing the right things, it will pay off down the track in 18 months, 2 years, and then, of course, forevermore after that.
So does proactive maintenance track PEW but then stop?
No. What that means, proactive maintenance is being ahead of the need for maintenance, so monitoring changes in machine performance. So we're going to work on the current machine as it is today. So we're going to be ahead of the failure curve and watching failure coming our way and then being proactively stopping that. That's fine for current assets, but I'm saying here the trouble starts at the design. If the design is the incorrect choice, then we might apply this and get good performance today, but it won't maximise the business success. So I want to have a process that picks up the design choices to get maximum profitability across the whole life cycle. So proactive maintenance is certainly part of what we're going to look at. We want to be ahead of the failure problems. We want to know what's coming, but that won't be as good as we can do because we can go right back to the beginning and do the what-if risk analysis on a drawing of the design and make the right choices out of the design. So proactive maintenance lives with the current design and we simply maximise this design's performance, which is good. It's a positive outcome. But we can do much better if we go right back to the beginning and make the better choices at the start and then still apply this on top of that also. So I'm not going to throw anything away that works. If it works, lean works, quality management works, proactive maintenance works. I want to take all those into a process that we lock that into our system of doing business. So what is successful in the past, I'm going to keep because it's successful. But I can do better if I take this life cycle concept into play. So I want to build a process of plant wellness and make that wellness a system of running our business. So I'm going to have some sort of flow chart that describes the early life of the machines, what we want the assets to achieve, what performance they must deliver, what reliability delivers that performance, what engineering standards, maintenance operating practices deliver that reliability, what's the plans and activities that we're going to have to implement, make that the plan we're going to bring into the company and make it a company's future practice, run that plan, see what the improvements are, and from these improvements, make more improvements. And we have a continuous improvement loop. And we want to drive change on purpose. We want to drive positive change. So we're going to be looking for experimentation. Now, what we do on day one and will not be sufficiently successful for the next coming years. So I want to have a way to make sure that we don't just sit where we are today, because we can improve the business for today, but the world's always moving. Your competitors, they won't sit there either. No. Right now, China's growing, India's growing, Vietnam's out there trying to get some work off the Chinese. So the whole world's driving towards lower and lower costs, and I can't just sit there with one solution. And no matter what I do in plant and equipment wellness, I've got to keep moving forward, and I'll introduce intentional changes. Gee, this might be better. I'm not sure if it is. Well, let's do an experiment. Let's do a 3-month trial and intentionally make the change and see what the effect is. So I'm going to use a Six Sigma thinking, looking for refinement and improvement in a structured, logical way to make sure that we just don't sit still and let the other guys catch up and run us over. So yeah, it'll be a life cycle issue from the design through to the actual operation. We may have to change our business structure. Remember, teamwork is a smart thing to begin to include. Now, if we are a silo mentality business, I'm going to have to question that, because silo mentality has got us to where we are today. It won't take us any further. Silo mentality, silo approach delivers the current outcomes that we're getting. That may not be sufficient. We have to start looking at a matrix structure. We have to start doing a lot more teams. So no more maintenance. It'll be the manufacturing team. That'll be the supply guys and the operations guys. So I'm going to be challenging anything of the past that we thought was good enough, because it is the past practices that are giving us today's results. And if today's results are not good enough, then it's because it's the processes we chose that we have to question. And I'm going to look at anything that works, that's better than where we are today. So the 3 T's and the accuracy consultant enterprise is to find out the processes that work, that give us a narrow distribution of outcomes, and lock those into place in the business. And knowing they won't be good enough in 5 years' time. We're going to have to improve those even further. But at least now I've got a technique that traps good practice and makes us refine it. And whenever you find a better solution, it becomes what we now start to do. Because if it's a better solution in my procedure, I'm going to rip the old one up and put a new one out there and begin using the better solution than what we had in the past. So yeah, the 3 T's is a simple technique, a simple way of thinking of how to capture better practice and then keep moving it forward into best practice. And it isn't far off the plan, do, check concept of what Deming introduced, of what Schwartz introduced. That approach of actually experimenting on purpose to find a better solution, smart business. Don't just lock ourselves into 40 years past practice. It hasn't worked for us. I want to challenge that and actually come up with a better idea, a better approach, and then lock it into place with the 3 T's. This particular slide is the number of techniques and methodologies that are available to us around the world. There are many things that companies are already doing. Things like preventative maintenance, planning and scheduling, materials management, occupational health and safety, shutdown planning. A lot of companies are doing good things. It isn't far enough. We want to go into the area here where we eliminate failures and we remove defects. It's because we allow and accept failures and create defects that we have these problems in the first place. So if I want to go from this area here of reactive type thinking to a world where there are few problems, where things don't go wrong in the first place, I've got to go through a number of barriers. There's going to be a skill barrier, because today's outcomes are the result of the processes that we currently use. And some of that will be because our skills are not good enough yet. So there's going to be a skills barrier, and of course, the human nature will be, you mean what I've been doing for 20 years is not good enough, and it's been fine for 20 years, and now you got me to change? So change and change management will be a real big issue with this, but got to move forward. And there'll be a skills barrier to confront, and of course, finally, there'll be a mindset barrier. Mindset of the OE, of the CEO, of the vice presidents, of the managers, of the supervisors, and of the guys. So I can't hide that fact that yes, this is a different way to approach things, and because it's different, there will be naturally a barrier put up by those who are doing it the current way. So if we're going to do plant wellness, we have to bridge these barriers in a way that people are willing to come along with us. I can't push them because they'll push back. You're going to have to come with me. We're going to have to come down this path together, guys. Here's the right way. We're going to introduce the right way, but together we're going to move down that path. And that's where the time takes. This is where the first couple of years are going to go. Upskilling guys, getting the right strategies into place, getting the documentation right, getting the thinking right. And until that barrier of the right mindset's bridged, until we can get guys to want to be in this world of defect elimination and failure prevention, it'll be an effort to get there. But once it's there, the payback is very obvious, because reliability just goes to the top and stays there. And everybody's really happy after that. The people involved, we can't walk past or can't walk away from the fact that we have to get people to want to do these things. So the idea here is we're just doing as we were trained to do, but that is giving us the results we're currently getting. So I want to have a path where we move up this scale to we become special, become more skilled, become specialists, have better procedures, high quality procedures, the three key procedures, become an accuracy controlled enterprise where I am now an expert in my area of expertise. So I know what that machine requires, understand the ISO count, understand about fits and tolerances, understand about alignment. I can do a great alignment. I'm professional at what I do when it comes to maintenance and when it comes to operation of my machinery as well. To the point that we become a team of experts. We're all working together across the business as experts in our area, and we're looking at this as a team. So there's a people aspect, there's a process aspect, there's a financial aspect. If we are currently doing basic accounting, we're just looking at some raw numbers and the numbers are looking bad, we go back and analyse the numbers. If we're working down here purely at an accounting level, we're missing opportunities because we aren't looking at how good things could be. This cost of failure. Now, what's the true cost of a breakdown in this company? Because if I'm costing $10,000 to repair direct maintenance cost, and the actual business cost is $100,000, there's $90,000 there that I never saw before. So my costing system has to pick up how much money I've left behind on the table, how much money is falling off the table. So my costing financial guys are going to have to move from simply costing hours and product and materials to how much money are we losing by not doing the best practice. Because if the financial guys can see there's absolute fortunes here waiting for us to get, and all we have to do is get the right process and the right techniques and the right skills, then we have a business case to make the change. So I've got to think about the change in the financial benefit of the company if I move from simply doing cost accounting down to understanding how much money we're losing and how much money I can make back by doing smarter things. Then, of course, we have one final thing, and this is the leadership. Now, I'm not keen about one person leading because then all we are is we're sheep. We follow the leader. And the future isn't about one person leading. It's about all of us being able to take on leadership responsibility and our area of expertise. Now, it becomes a thing I call situational leadership. In a situation where I'm the expert, I'm the leader because I know better than you what to do. So this leadership is going to move around to the people that are the right guys to lead this situation. Operational problems, the operations guy steps in and he takes leadership. Maintenance, I step in. Engineering, he steps in. Now, depending on the situation, we want to put the right leader in front of that team to solve that problem. So I've got to have guys that can take on that role. So there's a degree of all of us wanting to perform at a higher level of leading others because we know better than what they do. So yeah, there are 4 aspects that come into this entire holistic approach. I've got to have correct processes done properly and ones that actually deliver the outcomes we're after. I've got to have people that want to be on the journey, that want to make a better world. I've got to have the culture. I've got to have the practices, the techniques, the ways of doing things that are how we support that. Just naturally how we work is to produce low defects and high reliability. Then of course the finance side has to make sense as well. I've got to show where the money can come by applying right processes, skilling up our guys and having a culture of high reliability. So yeah, it's a holistic perspective because it's a life cycle issue from the very beginning of the first thought of what we're going to do with our business through to the guys that design it, operate it, maintain it. So I can't just work on a portion of a business. It's the complete perspective we have to look at because it's a business-wide solution. Whereas RCM, reliability centred maintenance, is a maintenance factor solution. It isn't a business-wide thinking. And so you limit yourself by locking it down to just this group or just that part of the process. And we want to have the whole business go forward. So we're down to hopefully a simple model of what plant and equipment wellness is. It starts down here by understanding the parts fail, then the machine fails. If I can control my parts environment, minimise their stress right down low, I will create reliability. My parts are going to fail because they are overstressed from distortion or they are fatigued from degradation. So I've got to start controlling degradation in the operating area and in the maintenance area, and distortion when it comes to rebuilding and running it and installing it. And then I'm going to have processes and procedures that involve precision maintenance, precision operation. I've got to control the environment that part is in. If my part is inside of the machine, then the local environment around it, the lubrication, the temperature, the interference fit, the distortion, the overload, I've got to control those, because the part breaks, then the machine fails. So I want to build from here, from this concept of minimising stress in my parts, through a series of activities right up to the actual business system running the company. What quality standards must I have to deliver the precision required to achieve that low stress? What engineering standards give me that? What operating practices give me these controls on distortion and deformation? So these, at this high level here, it's about the business processes and the systems the company uses to create this outcome. So when we analyse a company's assets, we keep pushing up our understanding from what fails it, what controls it, what processes must we use, what skills must we use, what engineering and maintenance and operating and financial practices must we adopt, what procedures and practices and documents and processes do we lock into place that then give us the asset management system that produces the results that we are trying to design.
Where would you put ACE3T?
Let me step on to the next step. The accuracy controlled enterprise is the complete system that captures all these.
Okay, so you wouldn't just put it in the top line?
No, the 3 T's you'd actually build at this level here, because what operating target must we run at to ensure that when the plant operates, it's a nice steady flat line. Pressures, flows, gravities, temperatures, whatever the case is.
So all of those are done to that standard ACE3T?
Yeah. Because the 3 T's are the target tolerance test that gives us the narrow distribution we're looking for. The 3 T's create that very tight distribution. So I've got to have the 3 T's. If I want to have a tight distribution, then I've got to have what is the target that I'm looking for, and how big a boundary will I accept, and then that setting those parameters sets the limit on my process. And of course the final T, the actual test, is to prove I'm within those boundaries. So yeah, we're going to use the 3 T's, or the concept of that, across all the documentation we're going to build. Up here is the documented systems and processes we're going to run the company with to create that reliability that results from low stress operation of our parts. Now tomorrow we'll talk about the 6 steps in the process, because it's all about recognising where the risk is in the machine, where the risk is to the operation from having those risks to the machine, controlling those risks in the operation and in the machine, introducing the right processes to control those risks, monitoring the processes that are actually working, and then ensuring we are always improving, looking to refine this boundary now narrower and narrower and narrower. Because the more precise I am, the more reliability I'll get, the more accuracy I get, and the less breakdowns and less problems result. So yeah, this one's a bigger triangle, and I chose triangles because triangles are the strongest structure in the universe. When you look at the strongest designs, everything's got a triangular shape. It's the strongest structure. So the concept of having a triangle made sense in building robust business processes that are strong, that support the business, that deliver the outcome that you want. So it's the same thing here. Here I've got more definition from those previous slides. So again, part health down to operating practices and maintenance practices, 3 T's and writing the precision requirements that are necessary, choosing the materials of construction. Now we're down to the design phase of that life cycle. Here we're into managing the actual operation with quality practices, supply chain control, lean practices. There are some good lean things that we don't even want to question. Just bring the good practice in. If that lean practice gives us low stress on our parts, go for it. Go for it, because that practice will create reliability. Why wait? And on we go into our business structure. So up here is all the things a business does that are built from the right thinking. Everything snowballs upwards into the processes that lock that result into place. Most companies go the other way. They build the business processes and hope the right results come out, which gets them where they are today, because everything depends on luck then. It's all hoping the right things are going to happen. He was saying, what are the right things to do to create the reliability and put the right things into place across the whole business, across the whole life cycle. So it's about maximising life cycle profit with markedly reduced human error and greatly increased work quality results by delivering the least maintenance commitment while producing world-class reliability that brings operational excellence performance through creating one single holistic business system to address life cycle cost issues and reduce variation and produce the lowest operating equipment risk profile that results in the least operating costs forevermore. So it's a methodology, a step-by-step process across the business requirements that produces maximum profit optimally. And that's what we're trying to build in their plant wellness way. Just one technique everybody uses that company applies in its situation that is right for that business.